Hi, this is Captain Tarrant, and this is a problem from NS301 stability, which we're going to just run through the solution now. So let's say you're given a ship, and your ship is 8,000 tons displacement, and the KM, you're given the KM here, 28.54, the KG, 24.93, and the following weights are then going to be loaded and or discharged depending on what the weight is. Now this problem is a little more complicated than ones that we've done in the past. So far what we've been doing is we've been mostly calculating the vertical center of gravity, but in this one what we're going to do is we're going to look at the effect of the loading and discharging, because we're going to load two items, we're going to discharge one, on not only the vertical center of gravity but the horizontal, the transverse center of gravity. Because when we finish doing all this, we're going to find that the vessel is going to have a list. And your task is going to be to calculate the final list. To do this, we're going to use the theory of moments. We're actually going to do the theory of moments twice. First time, we're going to do the theory of moments vertically. And after we do that, we'll be able to solve for GM. Then we're going to solve for theory of moments horizontally or transversely. And then from that, we're going to use the inclining formula. So we're going to do theory of moments vertically, use that to calculate GM. We're going to do theory of moments transversely, and then we'll take that moment and we'll stick it into that inclining formula, and we'll just do the step by step. So you'll notice, before we go on any further, there was no mention in this problem to use the stability data reference material. Which means that if you're not told to go to the book, the stability book, you should only use information that's in the problem. Okay, so this will make a difference later on, which we'll find out. So we're only going to use information that we see right here. If it's not here, we're not going to look it up, because this is not one of those vessels that are in that stability book. That stability book that you'll use, that we have, it has all the hydrostatic tables and all that, is for 3 particular vessels. This is a different vessel, so you can't use those tables. Okay, so let's calculate the theory of moments, TOM, okay, vertically. So weight times distance is going to be the moment. All right, we got an 8,000 ton vessel, okay, with a kg of 24.83, which gives us that moment for the vessel. We're going to load 250 tons at 20 feet. We're going to load 300 tons at 2 feet. And we're going to discharge 50 tons at 3.94 feet. So there is our total weights, 8,500, and our total moments, 20.204843. So our kg is going to be our total moments divided by our total weights, and that gives us a vertical kg of 24.10. So now that we've got that, well, let's just go ahead and calculate GM, because we're going to need it later on. So GM is going to equal KM minus KG. This formula right here is for a vessel with positive stability, and this vessel does have positive stability because kg is 24.1 and km is 28.54. So this boat is positively, it's got a positive GM, so that this formula is then appropriate. So we end up with a GM of 4.44 feet. Okay, we've done the vertical moments. Okay, now we're going to do theory of moments for the transverse. Okay, now look, let's look at the second part here. We're loading 250 tons, but for this 250 tons, we're loading at 25 feet to starboard of the center line. This 300 tons, we're going to load 20 feet to port of the center line. And here we're going to discharge something that was on the vessel that's 15 feet to port. Well, you know, this is actually, basically what we're doing here is this is like a seesaw problem here, okay? We've got, here's our little seesaw, and we're going to be adding weights to one side, adding weights to another side, subtracting weights from a side, and we want to see at the very end, how's the seesaw going to behave? In fact, the vessel's going to be inclined, and that's what we have to figure out, okay? Because we're going to find this actual list at the end. So what we're going to do now is theory of moments transverse. So now, this theory of moments works the same way, but because we've got weights on one side or the other, and we're not measuring really from the keel, we're measuring from the center line, we're going to use a new convention. If we load something, we're going to say that we have added weight. If we discharge something, we're going to say that we're subtracting weight. Now, we're also going to have to kind of keep track of whether it's on the port side or the starboard side. Now, there is a convention that is used in the United States, and that is that if the weight is loaded, if a weight is on the port side, we give it a plus symbol, and if it's on the starboard side, we give it the minus symbol. Okay, so let's look at this. We've got 250 tons, and we are loading it on the starboard center line. So let's go through this. First of all, we are loading, so that is plus. Okay, so there's that plus. Now we loaded it on starboard. Well, starboard by convention is going to be given a minus value. So it's 250 times 24.93. That's the distance. Actually, yeah, that should be a 2, not a 3. Okay, that came from up here. That's a little mistake. Let's not worry about it. Okay, so it should be 24.92. It was loaded, so it's a plus, but it was loaded on the starboard side, so it's a minus. So a plus times a minus gives us a minus. So it's a minus 6230. In fact, it's a moment 6,230 foot-tons on the starboard side. Starboard is going to be considered minus. So now what's the next thing? We're going to load 300 tons. Well, we should plus. It's going to be on the port side. That will also be plus. And then the weight will be 300 times 20. That's what we have. Plus for load, plus for port, 300 times 20 feet. That gives us a moment of 6,000. Now you can see right off the bat that these two moments almost cancel each other out. You're going to have 230 moments on starboard. Okay, the 6,000s cancel each other out. So this vessel is now going to start to incline this vessel somewhat to starboard. Okay, so now let's see what we do here. We're discharging on port side. Okay, so let's just keep track of our pluses and minuses. So we're going to, port side is going to be plus, but discharge is going to be minus, and it's 50 tons times 15 feet. So here you go. Minus for discharge, plus for port. Well, a minus times a plus gives us a minus. So we get a total moment, okay, of 980 foot-tons. And actually, if you go ahead, if you want to do all your weights would turn out to be 0 here, okay? If you actually do all the little math here as well. But we're actually not interested in this weight. We're only interested in this moment. After we do these activities, we're going to have a moment of 980 foot-tons to the starboard side, which means the vessel is going to be inclined to starboard. Now, why are we interested in this moment? Okay, or negative 980 foot-tons really means 980 foot-tons to starboard, because we're going to be doing the inclining formula. And the inclining formula for theta is weight times distance divided by displacement times GM. And then you do the inverse tangent of that, and you get theta. Well, this weight times the distance is this. This is what's left over. This is the inclining experiment, transverse, side to side, and we know that we're going to have a moment of 980 foot-tons to starboard. So this value that we have here is what's going to go here. The displacement we're going to take from over here, okay, which was 8,000. That's the vessel. At the beginning of the problem, we loaded 250, we loaded 300, we discharged 50, and GM is what we calculated right there. So theta is going to equal 980, or the moment, okay, the transverse moment, divided by the total displacement times GM, and when we do all that, you should get 1.5.